And welcome everybody to this lesson on giant covalent compounds. So we've dealt with small covalent compounds before, sometimes called simple covalent compounds, but today we're going to look at giant covalent compounds. So by the end of today, what you're going to be able to do is you're going to be able to describe the structure of giant covalent molecules. The three that you really need to know about are diamond, graphite, and silicon dioxide. You're going to be able to link the properties of diamond and graphite to the structure of the molecules, and you're going to be able to describe the structure of fullerenes and link this to their uses. So just a quick recap really. What you should be able to remember is that simple covalent molecules have only a small number of atoms. So when we say a small number of atoms, we're not talking one or two. I mean, some things might have tens or 100 atoms within the molecule. But when we compare that to something like diamond, which has millions of atoms within its structure, then we can actually say that simple covalent molecules have only a small number of atoms. Now, what this means is that they have low melting and boiling points. Okay, so here we go. So we've got low melting and boiling points. Okay, but it also means that well, they don't have ions, they don't have free electrons, so they cannot conduct electricity. Okay, and we know this because some of the things that we have looked at in the past are things like methane. Okay, now just so that I get you thinking, what I'd like you to do is when we look at a diagram like this of methane, there's something missing. So what I'd like you to do is just have a really quick think and go, right, okay, well, what is missing from this diagram? Okay, now what I'm hoping you would see is that actually what we are missing are some electrons. Okay, now what we then have is that, let's assume that we've got our central carbon atom and we've got a red dot in each. Now carbon is in group 4. It has 4 outer electrons. We are not interested in what is inside, but it has 4 electrons on its outer shell, and it's bonded to 4 hydrogen atoms. Now these 4 hydrogen atoms each donate 1, in this case this blue cross, 1 electron from each hydrogen. So we've got 1, 2, 3 and 4. And when we look at this, carbon has 2, 4, 6, 8 electrons in its outer shell, and hydrogen has 2 electrons in its outer shell. So carbon has completed its octet, and hydrogen has completed its outer shell, except because it's so small it can only have 2. Okay, and sometimes you will see these described as energy levels rather than electron shells, and that is why I've just highlighted that here. Okay, now this then is methane, and you might be asked to draw this in one of 3 ways. You might be asked to draw it as we've just done. You might be asked to draw it as these sticks, these lines between the molecules, between the atoms, or you might be asked to draw it just as kind of very simple dot and crosses between the atoms to denote that there is the shared electrons here. So I think we've pretty much covered simple covalent molecules just as a very quick refresher. What I'd like to do now is look at a giant covalent molecule. Now I've already mentioned it, but diamond is one of them. Okay, diamond is made up of carbon atoms only. So in our picture, each of these black circles represents a carbon atom. And because it is only carbon in there, we have carbon to carbon bonds represented by these lines. Now, what you can see here is that we've got a central carbon atom, and that is bonded to 1, 2, 3, 4 carbon atoms. Okay, but so's this one, and this one, and this one. In fact, all of the carbon atoms within diamond are bonded to 4 other carbon atoms. Okay, so, and here we've got just representing the carbon atoms and covalent bond. And it is this structure that gives diamond its properties. Okay, now diamond is extremely hard because of these covalent bonds. There are so many of them, and they are also very, very strong. If they're very, very strong, they're very, very hard to break. If they're very, very hard to break, then it means that diamond is going to be extremely hard. If the bonds are very, very hard to break, then the bonds give diamond a very high melting point, because to melt diamond, you're going to have to break at least some of these bonds. Okay? So to melt something, you have to break some of the bonds. To boil something, you have to break all of the bonds. Okay? So we're starting to see here that this is the structure of diamond. The thing is this is only a very, very small sample of diamond. In fact, there are millions, if not billions, of atoms within a diamond that you might find in a ring, for example. But I just don't have room to kind of draw them all on here. So, just as a quick recap then, diamond has carbon atoms only. Okay, each forms 4 covalent bonds to other carbon atoms, and that means that diamond has a huge number of covalent bonds. It's almost unfathomable, and this makes it extremely hard, and it gives it a very high melting point. We're going to compare that now to graphite. Graphite is also only made up of carbon atoms. Okay, so it's an allotrope. Okay, it's an allotrope of carbon. However, when we look at this structure, we've got this central atom here is only bonded to 1, 2, 3 atoms of carbon in this case. But this one is also bonded to 3, and this one, and this one. So the difference between diamond and graphite is that in diamond, each carbon atom is bonded to 4 other carbons, but in graphite, each carbon is only bonded to 3 other atoms. However, they are all bonded by covalent bonds. Again, same as last time, this is only a very small representation of the sheer number of atoms there are. What actually happens, you can see these are all hexagons, and these form in layers. And this dotted line represents the fact that we've got intermolecular forces between the layers, and they're forces, not bonds. They are not strongly held together. It is just through an electrostatic attraction between the layers. But because they are not strongly bound to each other, it means that they can slide over each other. Okay? And because they can slide over each other, it makes graphite very soft, and that is why you've actually got graphite in your pencils, because as you drag your pencil across the paper, you are actually sliding off some of the graphite from your pencil onto the paper. However, Because the carbon atoms in graphite only form 3 covalent bonds, each of those carbon atoms has a spare electron represented here by these red circles. And those electrons are not bound to any particular one carbon. Okay, they float around in this layer between the sheets of carbon atoms. They are said to be delocalized through the structure. Delocalized just means they are not attached to any one particular carbon atom. And because they are free to move then between these layers, graphite can conduct electricity. Because electricity is just the movement of charge, electrons have a charge, and the movement, therefore, of these electrons is enough to be able to conduct electricity. And we've seen this before in our electrolysis cells. When we've done electrolysis of sodium chloride, we use graphite electrodes. So just to recap then, that graphite has carbon atoms only. Each of them forms 3 covalent bonds to other carbon atoms, and that graphite forms layers which can slide over each other, which make it soft. And because it only has 3 covalent bonds, we have spare electrons which are delocalized, which means that graphite can conduct electricity. It can also conduct heat, but that's by the by. One thing that I'm going to touch very, very, very briefly on is this something called a fullerene, or Buckminster fullerene. Looks a bit like a football, shaped a bit like a football. We've got hexagons, we've got pentagons, but again, there are only carbon atoms here. They've been coloured in a slightly kind of weird, kind of orange, brown, yellow, kind of beige looking colour, with the bonds between them represented by these sticks. And these can be used for drug delivery. You can actually put drugs inside the cage and trap them until the body releases them. They can be used as catalysts. Again, you can put transition metals, precious metals inside. Lubricants. And you might also see them on tubes, like for example tennis rackets. But that is about as much as I'm going to touch upon fullerenes in this instance. The last structure that you need to know about is silicon dioxide. Silicon dioxide is found in sand. It contains a large number of covalent bonds, very similar to diamond, and it has a very high melting point. Okay, so the blue circles here represent a silicon atom, the red circles represent oxygen, and the lines between them represent the covalent bonds. So we have a silicon to oxygen bond, and then an oxygen to silicon bond, and then we have a silicon to oxygen bond, an oxygen to silicon bond, and it is actually shaped very, very similar to the shape of diamond. It's just extended because we've got oxygen in the middle between each of the atoms. Okay. However, because it is shaped like this, it has a large number of covalent bonds. And if we want to melt it, we have to break at least some of those covalent bonds, which are very strong. And because they are very strong, it has a very high melting point. Again, this is a very, very small sample of silicon dioxide. And that pretty much brings us to the end of this presentation. So, I hope you've enjoyed it, and I shall see you another time.